this video, we are going to be looking at molecular orbital energy level diagrams. When we're doing molecular orbital energy level diagrams, atomic orbitals of one element are shown on the left, for the other element are shown on the right, and molecular orbitals are shown in the middle. Dashed lines show which orbitals combine to form the given molecular orbitals. So for example, for Be2, the diatomic beryllium with a positive 1 charge, we're only looking at the valence electrons here, so we have the 2s and 2p sublevels for both. There's 1 2s and 3 2p's in both of my berylliums. The two s's combine to form a sigma 2s and a sigma star 2s. And then we also have sigma star 2px and sigma 2py and pi 2py and pi 2pz, and then the corresponding antibonding orbitals. Now this is a Be2 with a positive charge. Beryllium has 2 valence electrons, so we have 2 electrons in the 2s, and the other beryllium also has 2 electrons in the 2s, but because it's a positive 1 charge, we've removed one of those electrons. So when we go to fill it, we need to put 3 electrons in the molecular orbitals. And we're going to do that just like we do for the atomic orbitals. Start with the lowest energy first, 1 in each degenerate orbital before doubling up, maximum of 2, if there are 2, 1 up and 1 down. So we can put 1 up and 1 down in the sigma 2s, and we're left with 1 in the sigma star 2s. So this is the molecular orbital diagram for Be2+. This can be written in an abbreviated notation, well, without the lines, just like we say 1s2, 2s2, etc., except here we specify it's a sigma 1s has 2, sigma star 1s also has 2, sigma 2s has 2, and sigma star 2s has 1. So this is a way of showing where all of those electrons are without drawing out the entire molecular orbital. Notice that for everything up to the valence shell, all of them are filled. The bond order is defined as the number of bonding electrons minus the number of antibonding electrons divided by 2. Usually, a single bond with a Lewis dot diagram will have a bond order of 1 when using molecular orbitals. A double bond would have a bond order of 2, a triple bond, a bond order of 3, etc. This usually works, but not always. So make sure you are actually looking at the molecular orbitals and not just the Lewis dot structure. All right, this is showing the molecular orbitals for H2. Hydrogen has 1 electron in the 1s. The other hydrogen has 1 electron in the 1s. So we have the sigma 1s and the sigma star 1s, and both of those electrons can go in the 1s. So we have 2 electrons in a bonding molecular orbital and none in an antibonding orbital, which implies this is stable because there are more in the bonding than in the antibonding. If we look at bond order, the number of bonding electrons, 2, minus the number of antibonding electrons, 0. 2 minus 0 is 2. Divided by 2 gives me 1, so a bond order of 1, which we know there is a single bond between 2 hydrogen atoms. Well, hydrogen forms a single bond because it gets both of those electrons into the lower energy sigma 1s orbital. However, helium doesn't form a diatomic molecule. Now, we've said before that noble gases tend not to react because they have a full valence shell, which is true, but can we also explain it using molecular orbitals? Well, helium has 2 electrons in the 1s orbital for both of them. When those 1s's combine, I would have sigma 1s with lower energy and sigma star 1s with higher energy. When I go to fill up that molecular orbital diagram, I end up with 2 bonding electrons and 2 antibonding electrons. So for bond order, 2 minus 2 divided by 2 gives me a bond order of 0. So this molecule does not exist. When we get to the second period, there can be a little bit of an issue in terms of the order in which we have these molecular orbitals. The expected order would be sigma 2s, sigma star 2s, sigma 2px, pi 2px, pi 2py, and pi 2pz. So the sigma s, so sigma s, sigma star s, so bonding and antibonding for the s orbitals, bonding sigma for the p, bonding pi, 2 of them for the p, and then antibonding for the pi, antibonding for the sigma, is the expected order of those molecular orbitals. However, that only happens for oxygen, fluorine, and neon. Before that, the sigma 2px actually has more energy than the pi 2p orbitals. So instead of the normal order of having the sigma before the pi, we have the sigma for the s's first, but then the pi for the p, and then the sigma for the p. So the pi 2p actually have less energy than the sigma 2p for lithium through neon. So what this is going to look like is the normal expected order, which would be for nitrogen and up. I have the combination of the s's as I would expect, and then the combinations for the p's, sigma, then pi, as I would expect. However, on the beginning ones, I do have the sigmas for the s's first, but the sigma for the p has a higher energy than the pi for the p. So make sure when you're writing these molecular orbitals that you pay attention to whether the sigma p has less energy or more energy than the pi's for the p.